All right, so next we're going to talk about Newton's law of cooling. And actually, like the logistic model, I didn't mention this, but it's similar to the logistic model in the sense that I guess all of them sort of do. These come from solutions to something called differential equations, which way outside of the scale of this class, way outside the scale of a calculus class too, although closer to a calculus class than this one. And that's what we're going to talk about. Newton's law of cooling says that the temperature of an object after time t units is equal to some number times e to the kt. Wait, this looks really similar so far. Plus capital T sub s. This is actually a very, very similar model to what we've done before. Let's just look at what each of these things represents. Okay. And let's look at this thing too. So T of T is the temperature of an object after T units of time. A is a bit weird. Usually A is at starting value, but here it's not actually going to be the starting value. A is going to be the initial difference. Oh, looks like McDonald's now. A is the initial difference in temperature between the object and the room, or the ambient temperature. I didn't necessarily even mention what this is modeling. This Newton's law of cooling is like if I have coffee and I sit my coffee on the desk, how does that temperature of the coffee change over time? Like we know conceptually that eventually that coffee will become room temperature, right? Or similarly, right? If I have, if I take something out of the freezer, and I just put it on my counter, well, the object now is colder than room temperature. Eventually, it will warm up to room temperature. We can model that. We can model the temperature of these objects over time with this equation. All right. And K, like K is just before. It's just some constant. We're going to have to solve for K a lot. And lastly, T sub S is the ambient temperature. Okay. Again, the ambient temperature is like the room or the fridge or whatever, wherever it's sitting. All right, so that's how we can model it. Let's do an example and try to use this. Example 6. Some coffee, I don't actually drink coffee, but some coffee was forgotten about. And initially, this coffee was 180 degrees Fahrenheit. After 15 minutes, in a 72-degree room, whoa, I'm writing degree twice. The coffee was now 150 degrees Fahrenheit. Part A of this problem says write an equation that models this. And any time that we're looking at about an object with one temperature sitting in an environment that's another temperature, maybe it's room temperature, maybe it's a fridge, a freezer, a heater, whatever, that's going to be Newton's law of cooling. It could be called Newton's law of heating as well. It works for cooling and heating. Newton's law of heating doesn't sound as cool though. I have to stop making cool jokes are low-hanging fruit. Okay, we got to get better ones. So we're just going to use this formula. T of T equals AE to the KT plus T sub S and use what we know. We're going to save K for last. All right. Let's try to figure out the other things first. Let's look at A. A is the difference in temperature initially between the object and the room. So at the very start, what's the difference between the coffee and the room? 180 degrees minus 72 degrees. K, let's save that for later. T sub S is the ambient temperature. What's the temperature that the object is surrounded by? What's the temperature of the room? It's 72. So our temperature formula, if we subtract this out, is 108 e to the kt plus 72. And we need to figure out what K is. Well, there's one piece of information we haven't used. After 15 minutes in this room, the coffee was 150 degrees Fahrenheit. Let's say T is in minutes. And T, capital T, is in degrees Fahrenheit. And this says that the temperature after 15 minutes was 150 degrees Fahrenheit. Plug this in and solve for T. Solving another exponential equation, okay? So plug that in. We're going to get when is 150 equal to 108 e to the k times t. This case is 15 plus 72. Go ahead and pause the video right here. Get some practice solving exponential equations and see what you get as your value of K. Now what you should have done, subtract 72. We need that exponential function by itself. That's going to give us 78 equals 108 e to the 15k. Divide both sides by 108. And now our exponential function is by itself. We could simplify the left-hand side, but we're going to approximate anyway. We get the natural log of whatever this turns out to be equals the natural log of the right-hand side. They're inverse functions. Another way of doing this step is converting it from exponential form to logarithmic form. All right. Now divide both sides by 15, and that'll give us our K value. Whoa, I wrote K twice. Our K value is this. The natural log of 78 over 1 over 8. 78 over 108 all over 15 is negative 0.02169. So we have our formula. Our answer for part A is the temperature of this cup of coffee after T minutes is 108 e to the k times T plus the ambient temperature of 72 degrees. Let's see what that looks like on Desmos. Okay. Look at this. 108 e raised to the negative 0.02169T plus 72. For the x's, x is in minutes. So maybe let's look at 2 hours. And for the y's, y is in temperatures. Temperature. So maybe we'll look at, well, it started at like 180 degrees or something. We don't have to look all the way to 0 degrees. That's not very interesting. We can skip to 50 degrees. We can see, right, it starts at 180 degrees and it's cooling exponentially fast. But eventually it flattens out. It's going to eventually approach. We got that asymptote, which is going to be about 72 degrees. It'll eventually be room temperature. This is what our model looks like. And that's our answer for part A. Part B wants to know how long till the coffee is 100 degrees Fahrenheit. And again, you can solve this analytically. Plug this in to the function, right? This is asking when is T of T equal to 100 degrees Fahrenheit, right? How long wants us to solve for T? So you can do that. When is 100 degrees Fahrenheit equal to 108 e to the negative 0.02 169 T plus 72. Solve for T. We have the tools to do that. Or you just figure out, well, when is it equal to 100? About an hour, about 62 minutes. So if I ask you to do it by hand, if I ask you to show your work, if I ask you to calculate exactly, you'll have to do all the steps. But if I just want you to use the model and approximate, you can use Desmos or something like this. 62.2 minutes. A little over an hour. Part C. What will the temperature be after 2 hours? Well, what if I just plug in 2? When x is equal to 2, when t equals 2, rather. Whoa, all right, that's not what we wanted. We're going to plot the line x equals 2. All right, after 2 hours, it's 175 degrees. Hopefully you're screaming at your computer, your tablet, your phone, whatever, and saying, Jason, don't be a dummy. T is in minutes. 2 hours, that's 120 minutes. Okay, so it's going to be over here. For 2 hours, it's going to be about 80 degrees. So it's still warmer than room temperature, but you don't want to drink 80-degree coffee, I tell you that. Not 80-degree Fahrenheit coffee, not 80 degrees Celsius. Actually, maybe 80 degrees Celsius coffee. I don't know. I don't like hot things. But about 80 degrees Fahrenheit is our answer. But again, you could do this by hand too. What will the temperature be? That's T of T. Specifically, we want to know the value of capital T when little t is 120. That's how you use Newton's law of cooling. Good luck, and let me know if you have any questions.